you can tell X equal to plus 7. In this way, one can understand manganese in this compound, potassium permanganate compound, has oxidation state equal to plus 7. And other example, say potassium permanganate or sodium permanganate or sodium manganate, number of compounds we can take. Look at this. It is manganese compound only. Sodium manganate, potassium permanganate, sodium manganate, whatever it is. In this, sodium is familiar. Sodium is in our short list. Sodium is a metal in all compounds, has a definite oxidation state. Being an alkali metal, its oxidation state is always plus 1. Similarly, oxygen usually minus 2. Now you can guess what may be the oxidation state of manganese, like this. Here, 2 sodium atoms are there. Each plus 1 state plus 1 manganese atom. Each state only unknown. We want to find. And there are 4 oxygens. Each one in minus 2 state, we believe. So, as it is a neutral compound, total must be 0. Now, if we work out, you get X equal to plus 6. So, manganese oxidation number in that compound you say plus 7, here you say it is plus 6. And if you take a case, an example like this, Cr2O7 2 minus, just watch. In this, I took example for a compound. Compound, I say, because it is not having any net charge, whereas here it is called a compound ion. Compound ion means it is compound by more than one elements, but having a net charge. It is not a compound, it is a compound ion. In this case also, we can identify the oxidation state of an unknown element. Here, we understand oxygen known as minus 2 and chromium you want to calculate, say. But this time, net charge is not 0 because it is an ion. It has certain charge. So, simply what we do, we want to find this, say X. How many like that? 2. 2X plus 7 oxygens. Each we understand minus 2. And total this time not 0 unlike these because it is an ion. So, net we take as minus 2. It is a charge, it is charge only. So, X value you get here as plus 6. So, oxidation state for an ion like this, for a molecule, net oxidation state we know from the structure and any unknown elements oxidation number we can find. But this will be possible only if others are known. Because we believe that oxygen is known, because we believe that potassium is known, sodium is known, we could do this. Therefore, that short listed list oxidation states of elements which are of certain oxidation states, if you have in mind, this way oxidation states at once can be found. Like this, certain practice is needed for all of you. At home, you find number of examples in your textbook and all those you should practice, because this practice all depends on practice. There is nothing big to understand how to find oxidation state, because we have some elements with standard states and some other elements may not have like that. Different states may be possible, here plus 6 for manganese, here plus 7 for manganese, but that we can easily find. But for this little practice, and you must do practice such a way that we should not do like this big work. Yet once by looking at that molecule or ion, you must tell its chromium oxidation number plus 6 here, plus 7 here, then that application becomes very, very useful. So, this is how to find oxidation number of elements. Today, we continue the redox reactions based on how we find oxidation number of element as we have seen in the previous class. When we look at a reaction, one can understand that it is a redox reaction or not easily by observing these changes in oxidation number. Oxidation is loss of electrons, reduction is gain of electrons, but these electrons are not visible. So, when you look at the equation, you must understand whether any substance there undergoing some oxidation, reduction or not. For this, finding oxidation number which we found in the previous class will be helpful. Suppose I write one equation here. Potassium permanganate, FeSO4, ferrous sulfate, sulfuric acid, producing potassium sulfate, ferric sulfate, manganese sulfate and water. If we look at this reaction, there are so many elements. Potassium is there, manganese is there, oxygen, sulfur, so many are there, hydrogen. But how to tell whether it is a redox reaction or not? After knowing that, we can understand further about the reaction. For this, again the same short list will help you. What is that? We have a short list that some elements always have same oxidation number in all compounds. Some may change. In that we have seen alkali metals, alkaline earth metals, zinc, aluminium, silver and fluorine, and even to some extent oxygen, hydrogen. They are having almost certain oxidation states. Though sometimes like hydrogen and oxygen may be found with the different states, rarely. But in so many normal reactions, we find them, oxygen and hydrogen also, with their normal -2 for oxygen, +1 for hydrogen, regular states only. So we can use that to understand whether a reaction is a redox reaction or not. First, recognition important. Suppose here so many are appearing, but still we can tell which element is changing, which element is not changing. Let us see one by one. Potassium, we need not bother, because being an alkali metal, whether it is potassium permanganate or potassium sulfate, those elements like potassium have always same state, so we need not worry. Similarly, oxygen. Oxygen generally in all compounds has same -2 state. So though appearing everywhere, we need not worry about that because it is always normal -2 state. Similarly, hydrogen always +1, here also +1. So here if you notice, every element you need not worry about. Few elements are probables because oxidation numbers can change for elements if at all. That element may exist in different oxidation states. Here manganese is one such compound, variable valent. Iron is one such compound, element. Similarly, sulfur is such element, it can have different oxidation states. So at once we must understand, here we must think about manganese element, iron element and sulfur element. Next, out of these three again, sulfur. Sulfur is here to be ruled out. Why? Though sulfur can have difference in oxidation states, in this particular example you see, throughout it is in similar fashion. Sulfate, 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 sulfate. That means sulfur in same state in all these. We can understand by the compound's formula, sulfate only. So hydrogen sulfate, sulfuric acid, ferrous sulfate, there ferric sulfate, sulfate. So it is not a probable here. So now only two are left. One is manganese, other iron. So what I mean is, though it is a lengthy equation appearing before you, you need not worry about all elements there, because we know some of the elements are having a definite oxidation state, except here finally left manganese and iron. So when you come to that conclusion quickly by looking at the equation, deciding whether it is a redox reaction or not at once completed. How? Like this. Let us find oxidation number of elements. For manganese, we doubted them, manganese and iron, because remaining all almost certain oxidation state. Manganese oxidation number here I find as +7. Notice at once I put on head. Unlike step by step calculation we did in the previous class, we now need not do like that. You must be quick enough in telling it that once. At once it is to say +7 state. Same manganese here in a different state. Manganese here in MnSO4 a different oxidation state, because sulfate, a known radical. Sulfate is always known, SO4 2 minus. Therefore, manganese state one can understand, +2 state. Similarly, iron, here +2 state, just like manganese there, here iron +2, sulfate -2, so iron +2. Like that, if you calculate for this iron, you get +3. How you got +3? you can easily tell like in other cases, as sulfate is -2, 3 sulfates -6, and each iron therefore should be +3 because it is neutral. So +3. So by that we can understand manganese oxidation number changed, iron oxidation number changed, like this. Oxidation number changed means what to understand? That substance has either lost or gained electron. This is nothing but redox reaction. So any element's oxidation number if changed, you can say it is a redox reaction. Like this, redox reaction will be recognized. Further redox reactions, to understand, we can have a separate discussion on redox reaction, but today our very purpose to see these redox reactions is to decide N factor of a substance when acting as reducing agent or oxidizing agent. Now, if you look at this compound, it is an oxidizing agent. What we are saying is reactions are acid-base reactions, redox reactions, and hardly precipitation reactions. So, to decide the equivalent base, N factors we understand for acids in one way, the bases the other way. Similarly, for redox reagents, it is done